this video, I'm going to compute a tangent plane in two different ways. They're really actually the same way, but they seem different. Those two different ways are, on the one hand, the tangent plane of a surface is the graph of the linearization at that point, if that makes sense. And then on the other hand, you can compute a tangent plane by realizing the surface as the level surface of a three-variable function and getting a normal vector by computing the gradient. So I'll talk about both of these in the context of this one example. So, first solution. The method here is to realize that this surface is the graph of a two-variable function. And if that's the case, so if your surface is the graph of a two-variable function, in other words, if you can solve for one of the variables in terms of the other, then the tangent plane is the graph of the linearization. Is the graph of linearization. In other words, I'll remind you what the formula for the linearization of a function is. The tangent plane to z equals f of xy, so the graph of the function f at the point a, b, f of ab is z equals the linearization formula. The linearization formula is the thing that looks like the tangent line equation, just up a dimension using partial derivatives. So it's f of the point plus the x derivative of the point times x minus a plus the y derivative of the point times y minus b. Like I said, this is also called the linearization of f at ab. And if you want, you could also call it the degree 1 Taylor polynomial of f at the point ab. In any case, this surface that we're given, it is the graph of a two-variable function. It does take the form z equals some stuff. Which means we can use this formula to compute the tangent plane. I could let f be all that stuff on the right, x squared plus y plus x sine of y squared. Spit up all this information, and then we're done. So we need a couple things. We need the partial derivatives. I'll do that over here. The x derivative is 2x plus 0 plus the x derivative here is just going to be sine of y squared. Likewise, the y derivative is going to be 0 plus 1 plus, okay, so the y derivative here, leave the x alone. I'll get a cosine of y squared. And then by the chain rule, multiply by the derivative of the inside, which is 2y. Okay, so the tangent plane is z equals f of AB, in our case, is 1, 0, plus the x derivative of 1, 0 times x minus the x value is 1, plus the y derivative at 1, 0. And I didn't give myself much room here. Times y minus the y value, which is 0. Plug these numbers in and we're done. So continuing from over there, this equation is exactly z equals f of 1, 0. According to this, it should be 1, but let's check. 1 plus 0, sine of 0 is 0, so that's 1. Plus, the x derivative at 1, 0 is 2 plus 0. So it's 2 times x minus 1, and then plus the y derivative at 1, 0 is 1 plus, when y is 0, this whole thing is 0, so it looks like it's 1. So that's 1 times y minus 0, which is 1. All right, there we go. It's the tangent plane. Like I said, this first method was if the surface is the graph of a two-variable function, you can use the linearization. That's method 1. Okay, the second solution is to realize this surface as the level surface of a function of 3 variables. What's the deal there and why does this work? The key fact is that the gradient vector of a function is always perpendicular to level things. That could be level curves or level surfaces depending on the dimension of your function. Why is that useful? Because what are we trying to do? We're trying to find a plane. How do you find the equation of any plane ever? You need a normal vector and a point. So to find the equation of a plane, of any plane, you need a normal vector and a point. Well, we were given a point, so all we need now is a normal vector. And what we're going to do is the surface, let me draw in green. So this right here, rather than trying to actually draw a surface, I'll draw a heuristic picture a dimension down. Here's our surface. Here's our point. And what we're trying to do is find the equation of the tangent plane. We need a normal vector, which means I'm looking for a vector that looks something like that. Okay. The relevant fact that I said verbally about a minute ago is that the gradient vector of a function, capital F, is perpendicular to level things. So the goal here is to take this green surface, the equation that we were given, and I want to realize that as the level surface of some function, capital F. If I can write this as, say, capital F of x, y, z equals some constant number, that's exactly what a level surface is of a 3-variable function. Say capital F equals 0, then this fact tells me that the red vector that I'm looking for one way to generate such a vector would be to take the gradient. So we can take the gradient of the 3-variable function, that'll be the normal vector, and then we'll be in good shape. So how does that actually work? The first step is to break my chalk, and then the next step is to do this step in green, which is to realize this surface as a level surface. In practice, to do that, you just take all the variables in whatever equation you're given and move them all to one side. So in particular, I could take the z over here and subtract it to be on the right, and that's what I would call f. So I would start out by saying, let capital F of 3 variables be x squared plus y plus x sine of y squared minus z. The point being that that equation that we care about is exactly, so the surface we care about is then given by the equation this equals 0. Because if this equals 0, then you can move the z back to the other side and you get exactly that equation. All right, so our green surface is a level surface. Tells us that the gradient vector is perpendicular to this. Since the gradient of f is perpendicular to the level surface, a normal vector for our tangent plane is the gradient. So let's compute that gradient. We actually already have the x derivative from the, well, let's just do it again. What's the x derivative here? It'll be 2x plus sine of y squared plus 0. Same as the x derivative from the first part, no coincidence there. The y derivative will also be the same. It'll be 1 plus x cosine squared, x cosine y squared times 2y. And my vector is going to look a little awkward because I'm running out of room, but we have a third component, which is the z derivative. The z derivative of this expression is -1. So hopefully this isn't too awful to read. But 3 components, here, here, and here. This will be our normal vector. Now the normal vector we actually care about is that at the point 1, 0, 1. Plug that in, we've got our point, and then we're done. So I'll be careful. This expression represents the normal vector at any point x, y, z. The one that we care about is the gradient of f at the point 1, 0, 1. This is the vector. Again, the first 2 components we already computed in the first solution. This will be 2 plus 0, so 2. 1 plus 0, so 2, 1, -1. Normal vector, point, we can spit up the equation and we're done. So the equation of the tangent plane is finish it off over here. Is the x derivative, or the scalar in the x component here times x minus the x value plus 1 times y minus the y value. So that's just plus y. And then minus 1 times z minus the z value equals 0. That's the tangent plane. And as long as I did this correctly, this should be exactly the same as what we got in the first solution. Okay, so to summarize that second method, which is a slight change in perspective on this situation, I've got a surface. I realize that surface as the level surface of a 3-variable function, and then the gradient is the normal vector. This is something you can always do. So let me write that down actually. Remark, you can always do this method. You cannot always do what we did in the first solution, which is to realize that that surface is the function of a 2-variable function. That surface is the graph of a 2-variable function. That's not always going to be the case. For example, think of a sphere. A sphere fails any kind of vertical line tests you want to throw at it, so you cannot realize the sphere as the graph of a function. Therefore, computing a tangent line to something like a sphere, it's a better idea to do this kind of thing.